All right, we've got 2 more practice problems with using the first derivative to do an analysis for increasing and decreasing, finding critical numbers, and eventually we're going to be finding extrema in the next example. So I've listed the steps up here just as a little checklist for yourself as we go through and do this. We're going to start by taking the derivative of the function. So I'm going to have you pause your video and find the derivative of f of x using the quotient rule is my hint to you. Go ahead and pause your video. When you're done, come back and make sure you've cleaned up your answer. So pause now. All right, so little low d high minus high d low over low low, and then I cleaned up my answer. I got 32 plus 2x squared all over 16 minus x squared squared. Then it says set the derivative equal to 0, and also consider if the derivative is undefined. All right, well, if a function is equal to 0, so here we have f prime, we're setting this whole thing equal to 0. We're going to have, we really only care where the numerator is equal to 0. And the reason is, the first thing that I would do to start solving this fraction situation is I would multiply both sides by this denominator. And so I end up with 0 equals 32 plus 2x squared. So a shortcut is just worrying about the numerator. Well, if I go ahead and solve this, I'm going to get negative 16 equals x squared. So plus or minus 4i is equal to x. Well, that's not going to create any critical numbers then for us because we're talking about a real number line rather, a real number system. Then it says we also have to consider where this function might be undefined. Well, f prime, right, that's a function itself. F prime itself is a function. I want to just look at where the numerator is equal to 0 because we have major life problems in math when we divide by 0. So that's going to create our undefined situation. Taking a square root, adding the x squared to the other side, I get x squared equals 16, which means this time my critical numbers are plus and minus 4, which are both real. All right, so then we took care of that part. These critical numbers define intervals. Well, we're going to put those critical numbers on a number line. We had negative 4 and 4. From where our derivative was undefined. And then it says, test the sign of the derivative by plugging in a random number from each interval. Well, let's talk about these intervals. I've created one interval that's negative infinity until negative 4. I've created another interval that's from negative 4 to 4. And then I've created a third interval this time, which is 4 to infinity. So I'm supposed to pick a number from each of these and substitute into my derivative. I'm going to choose negative 5, I'm going to choose 0, and I'm going to choose 5. Doesn't matter what numbers you pick, you just want to pick one from each of these intervals that we've created, right? So I've got this interval, and this interval. F prime of negative 5. Well, here's f prime over here. If I sub in negative 5 to the bottom, this whole denominator is going to end up being squared, which means the whole denominator is positive no matter what. 5 squared is, negative 5 squared is 25, times 2 is 50, plus 32. That definitely comes back as a positive number. Remember, I don't care what the value actually was. I just want to know the sign of that interval. Okay? If I plug in 0, 16 minus 0, that whole thing squared is still positive. 32 plus 0 is positive, so this interval comes back positive. And then if I plug in 5, 16 minus 25, but that whole thing squared is still going to be positive. This numerator is also positive. A positive divided by a positive is still a positive. So what we ended up with is 3 positive intervals, which means that our function is going to be increasing on all 3 of those intervals. What you have to be careful of, though, is that you can't just group them all together because, hold on, let me write this in first. So increasing on negative infinity to negative 4, from negative 4 to 4, if you want to put your union signs in there, you can, and from 4 to infinity, because, and I'm writing out the full word because, not writing b/c, because f prime of x is greater than 0. So what I was going to say is you have to make sure you don't just say from negative infinity to infinity, because at -4 and at 4, f prime is not positive. F prime was undefined. That's what we got from this work over here. So you might be asking yourself, Ms. Schwartz, how is it possible that we have a function that's just always increasing but has these critical numbers? Well, if I were to sketch this as the original function, f of x, I'm going to have 4 and -4 is where interesting stuff is happening. The interesting stuff, the critical stuff, this time happened to be vertical asymptotes. So we end up with a graph that looks like this, in which case each one of these pieces, if you read from left to right, you have to walk uphill the entire time. The only time you're not walking uphill, so you're not increasing, so f prime is not positive, is where we have those vertical asymptotes that we would have to take a hop, skip, and a jump over. All right, our last one is going to be the same process. It just is going to result in the answer to a different question. So, kind of weird. But it says find all relative extrema. Well, extrema would be maximums and minimums. Thinking logically, a maximum is going to go where you started uphill and then you turned and went downhill. A minimum is going to be where you were going downhill and then you turned and walked uphill. So what we're really looking for are these critical numbers where maybe we've made a change, right? And they could be critical numbers because of being 0, or they could be critical numbers because of being undefined. This then also says sketch a graph and label the extrema. So basically we're going to start first by finding our intervals of increasing and decreasing. Just label these real quick. We're going to find our intervals of increasing and decreasing, and then we'll come back together. So pause your video to take the first derivative, set that first derivative equal to 0, consider where that first derivative might be undefined, draw a number line, test your values. See if you can do all of those things, and then meet me back here. Pause your video. All right, so here's all my work. I set the derivative equal to 0, and I got critical numbers of positive and -1. I considered where the derivative was undefined. Well, this is just a nice polynomial. We have no denominator concern, right, where we might have a discontinuity. So there are no critical numbers from the derivative being undefined. So I went through and I created my 3 test intervals, negative infinity to -1. I chose to test -2 into the first derivative. Then -1 to 1, I chose to test 0 into the first derivative. And then from 1 to infinity, I chose to test 2. Something that students often forget is they ask, well, where do I test these things? We're doing a first derivative test. So you want to test your interval number into the first derivative, which is why I like to write this f prime, showing that I'm taking a test value. All right? So what I came to my conclusion is that f of x is increasing from negative infinity to -1 and from 1 to infinity because f prime is greater than 0. I also found out that f of x is decreasing on -1 to 1 because f prime of x is less than 0. But this question said to find all relative extrema. So we just found something interesting, something critical is going on at -1. What we found is there is a relative, and we'll talk more about what this means, but relative max at x equals -1, that's where it happens, right, the x value, because f prime of x changes from positive to negative. So if f prime of x is changing from positive to negative, that's because the original function was changing from increasing to decreasing. And if you think about increasing, walking up a hill, decreasing, going down a hill, at -1, we reached the top of the hill. Now, we found something else is going on interesting at 1. This time we switched from negative to positive on f prime, so we would call this a relative min. At x equals 1. This time it'll be because f prime of x changes from negative to positive. My pen is starting to lag here. Right, so we were walking down a hill until 1. Then we started walking up a hill, so we got to a low point, a minimum on our graph. Okay, but then we just found out where this is happening, right? We have a relative max at x equals negative 1. But if I want to find the relative max height, or the relative max value, I need to find f of negative 1, which in this case is going to be equal to 5, because if you take negative 1 and put it back into the original function, we get 5. And this one then, if I wanted to know what is the low value, the relative minimum value would be f of 1, which in this case happens to be negative 3 if you were to substitute 1 back into the original function. So you can identify where things are happening using the first derivative, but then you figure out how tall or how small based on plugging back into the original. Yes, this is a lot of writing. Yes, this is a lot of justification, but this is what calculus is all about. It's about using math to justify what we know and the calculus behind it. All right, we're going to come back together as a group. We have a couple more things to talk about, and I will take a lot of questions over this. It's a lot of information, but make sure you have all of this written down for your examples so you can look back at your notes as we continue to work on this over the next couple weeks.